Okay, Chapter 9. Periodic properties of the elements. Dmitri Mendeleev, after whom is named Mendelevium, was one of the first people, one of the most important people rather, to order the elements on the periodic table. He ordered them by atomic mass, as we have it set up now, and saw repeating patterns in the properties. He came up with this periodic law that basically just states if you arrange them the way that they are on our periodic table, or similarly to that, you see sets of patterns recur periodically. Periodically just meaning every set number of, in this case, protons. You could also say we have elections in the United States periodically. That period would be 4 years. Every 4 years we've got a presidential election at least. We have other elections in between there. And based on the patterns that Mendeleev saw, he predicted some undiscovered elements. And when the atomic mass order didn't fit for other properties, he followed the other properties. So some of the predictions were for what we now know as gallium and germanium. And Mendeleev predicted things like atomic mass, melting point density, the formula of the oxides, the formula of the chlorides, so if you react them with oxygen or chlorine, and was pretty close on some of the properties, like density was a pretty near match, the atomic mass was also pretty similar, and the formulas of the oxides and the chlorides were also right on, which is great. Mendeleev's periodic law lets us predict what the properties of the elements will be. It doesn't explain why the pattern exists. Laws state what happened, theories state how or why it happens. Quantum mechanics, however, being a theory, can help explain why the periodic patterns exist. And if you know why something happens, then that can also tell you what will happen. Not all the time, but a lot of the time. To start off, we're going to learn electron configuration. Very quick coverage of orbital diagrams. So if you haven't covered it before, you might need to spend some extra time either in office hours or in lab or something else with tutors getting this stuff down. So our quantum mechanical theory we're talking about with all of the different shapes, right? That describes some of the behavior of the electrons. Our electrons exist within orbitals like the px, py, pz, s, dx squared minus y squared, etc. orbitals that are within a subshell. And the way that those orbitals are occupied is called an electron configuration. It's just where are the electrons. Typically, when we're doing an electron configuration, we're going to be talking about a base state, a lowest energy state. We'll talk about that on future slides. And we're also not going to really be talking about the orbitals specifically. For a diagram, an orbital diagram, we will, but for electron configurations, we're going to be talking our N and our L, or N and subshell. So here, 1s1 for hydrogen, 1 is our N, and S is our subshell. For angular momentum, quantum number equals 0. And we just have one electron in that orbital. And we can add many, 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 many more terms after this when we get to things that have more electrons. So the way that electrons occupy orbitals, in hydrogen, the electron occupies the lowest energy orbital in the atom. This is going to be the 1s orbital. That's our lowest energy orbital across the board. You can't solve Schrödinger's equation, which is calculus stuff, for multiple electrons exactly. You can kind of get it close. You can get an approximation. But you can't solve it exactly. And there's two other things that affect multi-electron atoms. We have electron spin. I believe that was m sub s, which has values of plus 1/2 or minus 1/2. Also up or down. Up corresponds to positive 1/2, down corresponds to negative 1/2. And that's a property of the electron. And we also have energy splitting of sublevels. You can also read sublevels as subshells. And we'll be talking about these more on the next couple of slides. So the first one up, electron spin. I talked a little bit about orbital diagrams. I typically will not draw them in like we see them over here on the right. I'll just use a single line along the bottom instead of drawing the whole box because I don't want to write as many lines. So we use boxes or, in my case, little lines like this to represent an orbital. For the 1s, we just have the one orbital. And we can use half arrows, so we just have half of it, or a spear to represent each electron in the orbital. This electron has the spin quantum number of plus 1/2. It's just a conventional thing. That's how people decided to do it, and so we do it that way. And we would call this upspin and downspin. Those are formal terms, if you can believe it. If you have a bunch of hydrogen atoms, they're going to be split between upspin and downspin about evenly. So it's not that they're always going to be upspin. We just typically draw them with upspin, or at least I do. And we can do orbital diagrams for multiple electrons as well. An important thing to talk about when we talk about orbital diagrams is the Pauli exclusion principle. No two electrons in an atom may have the same 4 quantum numbers, which is a little bit more confusing than it needs to be. So we can break that down to be a little simpler. So if 2 electrons are in the same orbital, they have 3 identical quantum numbers. That will be n, their principal quantum number, L, the angular momentum quantum number, and m, is that the magnetic quantum number? Anyway, they would have all of these 3 things representing a specific orbital, so like the 1s or the 2px. And the 4th quantum number, spin, must be different. So basically what this says is each orbital can have, at most, 2 electrons. They must have opposite spin. And that's basically what's written there in italics, but it's a little easier to find if I write it out. Some examples of orbitals: 1s, 2px, the dumbbell that's along the x-axis, 3dx squared minus y squared, which is the one that's flat in the xy plane, and the lobes are along the x and the y axis. Just to name a couple. So that's what we mean when we're talking about orbitals here. If we know the number of orbitals in a sublevel, that can allow us to determine the maximum number of electrons in the sublevel based on the Pauli exclusion principle. Because each orbital, each individual shape, can hold 2 electrons. So based on the number of orbitals we have, we can figure out how many electrons we can have within that sublevel or subshell. So our P sublevel has just the 1 orbital, it's the round sphere, that can hold a total of 2 electrons. Our P sublevel, the dumbbell shapes, has 3 different orbitals. Those can hold 6 electrons. Our D sublevel has 5, and so it can hold 10 electrons, and F has 7, so it can hold 14 electrons. For helium, here's what our quantum numbers would look like. Helium has 2 electrons. Both electrons fit in the 1s orbital. And so our orbital diagram, we've got one with upspin and the other with downspin, complementing each other. Our 4 quantum numbers, they have the same quantum numbers for n, l, and m sub l, and they just differ in their spin. They're in the same orbital, but with opposite spins. So they're very similar quantum numbers, and they only differ in their spin, up or down, which we represent with the orbital diagram. We can do this with as many electrons as we can fit in an element. One of the other things that we talked about is that sublevels get split. So sublevels and sublevels being things like S, P, D, F. So each of those letters in each n number for hydrogen all have the same energy. The orbital energy depends only on n. Orbitals with the same energy are called degenerate. I don't know why they're called degenerate. That's not the only term that we'll be hearing today that I don't particularly love. For multi-electron atoms, the energies of the sublevels are split, not degenerate. So if we're comparing S, P, D, and F, those have different energy levels even within the same n number, due to things like charge interaction, shielding, and penetration. Or it sort of looks like overlap would also work for that, but that's what it's called. In general, the lower the angular momentum quantum number within a principal level, the lower the energy of the orbital. So if we get up to our n equals 3, 3s is going to have less energy than our 3p orbitals. But 3px, 3py, 3pz have the same energy. That's the degenerate part. So we've got 3 energy levels, 3 orbitals that are at the same energy level, but our s orbital is going to be a little bit lower in energy. And we've got a visual representation of that also, but not on this next slide. It's coming up. Do we have questions so far? Right. Coulomb's law also applies here because we're talking about charged particles. So Coulomb's law states that the potential energy E of two charged particles depends on their charge, Q1 and Q2, and on how far away they are from each other, R. We know that this is true if we've played with magnets. The closer the magnets get together, the harder it is to pull them apart. That's sort of what's going on here. If you get two positive ends of magnets really close to each other, they're going to have a lot of energy against each other. It's really hard to push them together. If you flip them so that one's positive and one's negative, they really want to be next to each other. So for like charges, our E is positive, the charges repel. So two positive or two negative charges. Those are going to repel. The Q1 and the Q2 would both be positive or both be negative, and so that's going to make E positive. For opposite charges, E is going to be negative because we're going to have one positive and one negative charge. So when we multiply those terms, we'll end up with a negative E. Some other trends. We also have pi, and I think this, I think it's an epsilon sub-zero. I think that's a constant. The potential energy, the E, is going to increase if the particles get closer together. So if R is smaller, E is bigger, because we're dividing by a smaller number, so that's going to make the overall thing bigger. And the strength of the interaction, our E, is also going to get bigger as the size of our charges increase. So more charge, more attraction or repulsion. You can work those out either from the example here or just thinking about magnets. Strong magnets attract each other more. The closer they get together, the stronger the repulsion or attraction is. This sort of comes into play with shielding of the electrons and effective nuclear charge. So if you have a multi-electron atom, we've got multiple layers of electrons. And within those multiple layers, we're going to have attraction, which is positively charged, and repulsion by other electrons in the atom. So we've got some competing forces. And these repulsions can cause the electrons, particularly in an outer shell, to have a net reduced attraction to the nucleus, because that's what we call shielding. So we've got a layer of, I'll draw a picture. We've got our nucleus, and we've got a shell, let's say of 2 electrons. And outside of that shell, we might have another electron. This outer electron is going to experience the repulsive charge of these blue electrons. It's also going to experience the positive attractive charge of the nucleus, and those are offsetting forces. I'll figure out how to write someday. The blue electrons in this diagram repel the green electron, which offsets sum of the nucleus attraction. And we'll draw some arrows. These are the blue electrons, and this is the green electron. So the effect of that shielding, the effect of that offset of the charge, that's what we mean when we talk about the effective nuclear charge. This is the force that the electron actually experiences. In this case, we're talking about the green electron. So the green electron only feels whatever the nuclear charge is minus 2, because we've got those 2 electrons shielding it. All right. The closer an electron is to the nucleus, the more attraction it experiences. This is that R in Coulomb's law. Put my thing on Do Not Disturb. So the closer the magnets get to each other, the stronger the attraction. And also, the better that an electron, outer electron, is at getting into that electron cloud of inner electrons, the more attraction it'll have for the nucleus. So we're going to look at that radial distribution function that we saw last time. We also had the radial probability. That was the worst one. So the degree of penetration, how well it can get into inner electron shells. How likely it will be in inner electron shells is related to the radial distribution function. The better distribution function, or probability. We'll write probability to be different. That was the second one that we looked at when we were talking about distributions and probabilities. So here's a little bit of that shielding. This is basically what I drew. So our nucleus in A, our nucleus has a 3 positive charge. This would be lithium. So lithium's got 3 protons in here, and it's got 3 electrons. It's got 2 of those electrons in the 1s, the smallest little orbital, and they're typically going to be found in that smallest little orbital. And so this outside electron is going to experience a net charge of about 1+, because we've got 3+ and 2-. That'll cancel out partly to give an overall experienced force of 1+ for that outer electron. Where the penetration part comes in is this electron, that one that was experiencing a 1+ earlier, will sometimes be found within this inner electron orbital. Not most of the time, but some of the time it will be found in there. And when it's in there, it's going to experience more of the electron charge. And there is a graph showing the way that these overlap. Questions so far? All right, here is that distribution. We've got a couple of things going on here. We've got, on our x-axis, we've got our radius, our distance from the nucleus. On the y-axis, we have our total radial probability. So the higher that is, the more likely it is to be found there. And we're showing 3 different electron groups here. So we've got our 1s orbital. That's the one that's going off the graph. It's very likely to be found at this close distance, definitely below 200 picometers. We also have our 2p and our 2s orbitals, our next 2 highest energy orbitals. And we can see for the 2p, there is some overlap with the 1s, but it's mostly its own thing. It doesn't have a little node where it comes down and dips in probability like with our 2s. Our 2s has this big bump that's hiding under the 1s. And because of that, it's more likely to be found in this 1s orbital as well. Not most of the time, just compared to the 2p, we've got a higher bump here, so we're more likely to find it in that 1s orbital. And so we would say that the 2s has better penetration into the 1s orbital because of that. Another way that you could think of this is think about the shapes. Our 1s orbital is a sphere. Our 2s orbital is also a sphere. Our 2p orbitals are kind of like oblong dumbbell shapes. Those aren't going to overlap very well with our 1s orbital. So another way to think of it is that they're the same shape. So you're going to get better overlap. Even though it's a larger shell, we're going to get that better overlap. So that would be another way to think of it instead of thinking about this graph, which I'm guessing most of you won't be thinking about anymore as soon as we move on. So because of that penetration effect, because of that overlap effect, those electrons being able to get into lower energy orbital spaces, the sublevels, S, P, D, F, of each principal level, n equals 1, 2, 3, etc., are not degenerate. They have different energy levels. So our 2s and our 2p have different energy levels. In the 4th and 5th principal levels, n equals 4, n equals 5, those penetration effects become so important that our 4s orbital is lower in energy than the 3d orbital. So because of it, those electrons occasionally being inside of a lower energy orbital shell and experiencing more effective nuclear charge, that causes them to have an overall lower energy than the 3d orbitals, which are bigger and don't have as good of overlap because they've got those weird shapes, the 4 lobes or the 2 lobe with the donut. Those don't overlap very well with the spheres. There are other ways to remember this ordering, but this is why that ordering occurs, is because of that overlap. Here's one way that you could remember the general order of orbitals. So we have one axis here, just energy. The lower that it is, the lower the energy is. This is probably not a super representative scale. We don't have an x-axis. It's just ordered by S, P, and D. They're separated out so that you can kind of categorize them in your mind and to give them some space. So our 1s is the lowest, next 2s, 2p, and so on and so forth. And on that previous slide, we were explaining why the 4s comes before the 3d. It's slightly lower in energy because of its overlap with the 3 previous s orbitals. The way that we fill up orbitals is from the Aufbau principle. Aufbau apparently comes from the German aufbauen, to build, just meaning that we work our way up, lowest energy to highest energy. So the way that our electrons are going to occupy orbitals is to minimize the energy of the atom. Realistically, the reason that they would order this way is because lower energy is more stable. So they're going to fit the most stable energy configuration. So our lower energy orbitals, 1s for example, fill before higher energy orbitals, like 3d. Orbitals in the same sublevel have the same energy, like 3dxy, 3d yz, etc. And you are welcome to, if you'd like to, just memorize the filling order, but there's other ways that we can come up with it too. There are tricks. To remember the order. And if I don't mention any of them, let me know. From our exclusion principle, our orbitals, like 3dxy, 3dyz, etc., can hold only 2 electrons each, and the spins have to be opposite. This brings us to our second rule that has to do with degenerate orbitals. So when we're filling degenerate orbitals, we fill them singly first with parallel spins. You hopefully know what parallel means, but that just means that they're all matching. So as long as we've got an empty orbital, we're going to add into an empty orbital before we pair up with an opposite spin. And this is our second important, or one of our other important rules for electron configurations and diagrams. One way that we can think about the way that we'd fill up orbitals, if you'd like to apply it to something that's a little bit more tangible, something that you can imagine, rather than little E minuses filling up little boxes in like a one-dimensional grid, is the quantum hotel in my mother's chemistry land. So this is a pyramid scheme in that it's an upside-down hotel. So we've got one room on the lowest floor. And as we add to each floor, we get additional letters. and the letters stand for rooms. So the S is a single room. You've got one bed. The P has 3 beds. The D has 5 beds. And the F has 7 beds. So the beds is like the number of orbitals that we have. And you can only fit 2 people per bed. They're doubles or queens. They're not California king-size beds. So you can only get 2 people or 2 electrons per bed, and they have to have opposite spins. They're sleeping head to foot. Maybe they're like junior hires, and so they're weird about sharing a bed, so they sleep head to foot. And the way that the Chemistry Lane Hotel works, since it's this upside-down pyramid, you get really great views from each floor. And so staying in the first floor, it doesn't have a very good view. It doesn't cost very much. They're going to fill up that room first because these electrons are cheap, and so they don't want to pay a lot. But if the 1s is full, then they'll have to jump up to the second floor. They'll have to pay a little bit more. They'll have to have a little bit more energy to be able to stay in that floor. And that is true as we keep going up in higher floors. You don't have to use this if you don't want to. It's just if it's helpful, then that's great. And here's that energy diagram. Another thing about quantum hotel. So we just learned Hund's rule. We fill the electrons in first, then with parallel spins. Let's say that we're staying at a hotel room, not an S room, a P room that has 3 beds. If you and 2 of your friends go stay at a hotel room that has 3 beds, how are you going to arrange yourself in those 3 beds? You're not all going to pile into one bed because there's not enough room probably. You're probably not going to do in one bed, 2 people in another bed and leave an empty bed. You'll probably all say, great, we each get our own bed. That's why we got this room, right? So those electrons are going to spread out. Why did I write 2 A's? They're going to spread out when possible in those beds. And then if there's like 5 people in a 3-bed room, then you're going to have to double up 2 of those beds. So that could also be helpful for thinking about electrons, orbitals, etc. Questions? All right, we're sort of zooming, but we could be zooming more. That's okay. When we're talking about electron configuration, we're talking about the ground state in contrast to the excited state. We talked about the excited state a little bit, bumping an electron up to a higher n level with some energy, and then when it drops back down to a lower energy level, it emits a photon. So that was excited states. We're talking about everything in its lowest energy state, always the ground state. The number of electrons in a neutral atom is equal to its atomic number, because it's neutral. The atomic number is the number of protons. In order for it to be neutral, it has to have equal positive and negative numbers. Another helpful point is that electrons with parallel spins, because they're matching, there's a little bit of stability that comes with matching, with having that same spin state. And of course, our orbitals can hold a maximum of 2 electrons. So the electron configuration lists the sublevels in the order of filling, with our number of electrons as the superscripts, the little numbers that are raised. For krypton, we have 36 electrons, and either from memorizing all of our energy orbitals or some other way, we've figured out that it's filled up in this order. And we would place all 36 electrons. That can get really annoying. Krypton's only number 36, but it's already quite long. This would take a while to write even for me, and I can fill them up very easily because I know the tricks. So a shorthand way of writing out something that's long and annoying like this is the inner electron configuration or noble gas configuration. So we can write the symbol of the previous noble gas. That will be behind on the periodic table. Just like if you're sitting somewhere in the middle of the plane, your emergency exit might be behind you. So our electron configuration for rubidium, which is one further, so we find krypton over on the far right, is 36. Rb in period 5, number 37. Right, we've just added one more electron. And rather than writing all of this, we can abbreviate everything from 1s2 all the way out to 4p6 by just writing the symbol for krypton, Kr, in brackets. So that drastically shortens the amount of time that we have to spend writing out these electron configurations. You can do that for anything past helium. So that's super helpful. Here's some electron configurations and orbital diagrams. So our symbols, lithium, beryllium, boron, carbon. We're working through our second period on the periodic table. They have their full 1s orbital, and they've got some electrons in their 2s. 2s comes after 1s. For lithium, we've got one more electron, so we write in one up arrow. For beryllium, we have an additional electron, so that has to go in with downspin because we only have the one bed in the room. Once we get to boron, we have to buy up into the nicer 2p room, and we've got 3 beds. We can just put our electron in any one of those beds. Opposite spin. And then for carbon, 100. We have matching spin. So we're filling these orbitals in singly first with parallel spin. Write out the orbital diagram for argon and also determine the number of unpaired electrons. So in boron, we had 1 unpaired electron. In carbon, we have 2 unpaired electrons. So just things that don't have a matching down arrow for their up arrow. I'm going to start writing in some of the boxes. All right, orbital diagram. So I drew out all the boxes that we're going to need. For argon, we have 18 electrons. We're going to fill them in lowest to highest energy level order based on the Aufbau principle. So we can just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 electrons placed at this point. Another 1, 2, 3, 4, 5, 6, 7, 8. How many unpaired electrons do we have? We have 0 unpaired electrons. Questions about the orbital diagram? The cool tips and tricks are still coming. They're on the way. I didn't get same-day delivery. Okay, also relevant for talking about electrons and talking about electron configurations, we have two ways that we can categorize our electrons. We've got valence electrons, or outside electrons. So these are the ones in our highest n level. If we're doing an electron configuration with that abbreviation, so like we saw earlier with rubidium, Kr5s1, the 5s1 is our valence electrons. In this case, it's just one valence electron. So that's our outermost shell. The group number for our main group elements, if we're using the A designation, that corresponds to the number of valence electrons. We look at our periodic table. The one that we have in class is numbered just with regular group numbers. So we've got 1, 2. If we skip over all of our transition metals, those ones would be numbered with a B. If we skip over to 13, 13 is 3A, 14 is 4A, 15 is 5A. So if you just take off the 1 in front, that'll tell you the number of valence electrons. So oxygen is in 16, which would be 6A. Oxygen has 6 valence electrons. Fluorine's in 17, which would be 7A. So it's got 7 valence electrons. Any of our electrons that are in lower energy levels, so for chlorine, as an example, that's going to have electrons in our n equals 3. All of our core electrons are going to be in n equals 2 and lower. In this electron configuration example with rubidium, where we have krypton in brackets, krypton represents all of the core electrons. And one of the reasons we're talking about valence electrons and core electrons is that valence electrons are one of the more important factors in how our elements behave. So here's looking at our main group elements. We've pulled out the transition metals in the middle. Each of the elements in a column has similar chemical properties because they have the same number of valence electrons. So for example, lithium and sodium both form 1+ ions because they're in the same group. They have the same number of valence electrons. Beryllium and magnesium, it's the same, and all the way across. They have similar properties because they have similar or the same number of valence electrons. Generally, we can say that the valence electron count determines its behavior, and it also affects some other properties. So the reason our periodic table is laid out the way that it is because of those valence electron counts. It makes it very easy to look up and down a column, and once you know this, and figure out, okay, well, this is going to behave this way because of where it is on the periodic table. So there's a lot of like hidden tips and tricks built into the periodic table that makes it super helpful for people who know how to navigate it, who know the tips and tricks. Write an electron configuration for phosphorus. Identify the number of valence electrons as well as which they are, and the number in which are the core electrons. Our energy level order is this. So it's part of your electron configuration. You just have to fill in the superscripts. How many electrons does phosphorus have? How do we know it has 15 electrons? It's the atomic number and it's neutral phosphorus. So it must have 15 electrons. So using our electron orbital order here, we can fill each of these up. Each of our s orbitals is going to get 2, and our 2p can get 6. That's 10 electrons so far. We've got room for 5 more. We can put another 2 into our 3s to fill it up, and that means we'll have 3 left over to put into our 3p. So our valence electrons here are the ones in blue, because these have the highest n number. That's the highest n number that phosphorus has access to. That means that the other 10 are going to be core electrons. And we could confirm that we correctly did our electron configuration by checking the number that it's in, the group number that it's in. It's in 15, that would be 5a, so it should have 5 valence electrons. And that's what we came up with in our electron configuration. So that means things went well. You can also use that as a shortcut for filling up your electron configurations if you use the noble gas shortcut. So we could have done Ne in brackets, and it's in the 5th group, so we would have 5 electrons. And we would put those in 3s, then 3p. So we'd come up with the same thing. You could have also taken the 15 and subtracted the 10 electrons that neon has to also come up with 5. Questions? All right, here's where we get into some of the shortcut stuff. So the periodic table we can divide into 4 blocks representing our 4 different sublevels, S, P, D, and F. The group number, the column number of a main group element is equal to its valence electrons for that element. Take off the 1 in front for things that are in that far right group. And the row number, or the period, of a main group element is equal to its highest principal quantum number for that element. So if that element is 10, 10 is in the main group. N equals 5. The periodic table that we have in the class has the period number on the left column. Otherwise, you can just count down. So we find 10 in our 5th period, so it's going to be N equals 5. So that's where all of our valence electrons would live. And here is our 4 blocks. So our 4 orbital blocks, we have the S block, on the far left. Helium's also in the S block, or counted in the S block. We have our P block, that's the right side of the periodic table. Our D block is all of our transition metals. And the F block is the lanthanides and actinides that we don't really talk about because they're weird. This is the method that I would recommend for learning the orbital filling order. It's as easy as reading off from the periodic table, as long as you know that we've got the S block on the far left, the P block on the far right, and the D block on the middle. You can do pretty much all of them for free super fast. So if we want to write electron configurations using the periodic table, we can, of course, use our shortcut. So doing it for chlorine, our inner electron configuration, our core electrons, come from the previous noble gas, neon, and then we just read left to right across our periodic table. So we're in row 3 now. We are past our S block. That means we've got our S block filled, so 3s2. And we are in our P block. We are in the 1, 2, 3, 4, 5, the 5th spot in the P block. That means we have 5 electrons in the P block. So that's 3p5. And that would be our electron configuration. And it can be that quick for any of them on the periodic table, assuming that they're not in the lanthanides or actinides. Those take a little longer. Questions about how that works? Another important thing to remember, what's the n number for our first d orbital? 1, 2, 3, 4, 5. Those would be the n numbers for D. It's not 5. We have a quantum number that corresponds to our sublevels. Does anyone remember what that is?
3 for D.
It is 3 for D. Why is it 3 for D? There's a couple of ways that you can remember it. So one approach is with quantum numbers. D is L equals 2. Our range for L is 0 to n minus 1. So L equals 2 shows up first in n equals 3. That's one way you could think of it. You could also maybe remember that for our n numbers, 1, 2, 3, 4, etc., the number of subshells is the same. And S comes first, P comes next, and then in n equals 3 we unlock D. In n equals 4 we unlock F. So the top row of our D block is what n number of D? This whole row is 3D. And what period number, what row number does it show up in? 4. So you may end up running into trouble if you don't remember that 3D is the first place that it appears, and you count appropriately beyond that. Another way that you can remember is that the D is 1 less, so 3D in the 4, it's 1 less than our row number. For our row number. So D is n minus 1. For the F block, it's 2 less. All right, use this periodic table to determine the electron configuration of bismuth. How are we going to start our electron configuration for bismuth? With a shortcut. What's our shortcut? Yeah, the previous noble gas in brackets. That's xenon. So putting xenon in brackets covers everything in n equals 5 and up, so we don't have to worry about that. So we can get on with our n equals 6. So we'll start in row 6. What block are we in? S. We start off in 6, S. Are we past the S block? Yes. How many electrons fit in the S block? 2. It's 2 wide, just like 2 electrons wide. We can fit 2 electrons in there. And then we get to our transition metals, which are what? The D block. And what's our number going to be for that D block? It's going to be 5D. Are we past our D block? We sure are. How many electrons fit in the D subshell? 10. Conveniently, it's 10 elements wide. And we are finally into what block? Our P block. So what's our number going to be for our P block? 6P. What position in the P block are we? We're in the 3rd spot, so it's 6P3. And how many valence electrons does bismuth have? Do we expect it to have? It has 5 valence electrons. The d orbitals here don't count because they're 5d. So when we're working across the d block, we're actually filling in core orbitals. And there's some weird stuff that happens in there as well sometimes. I had a thought. I don't remember. Oh well, I'll probably remember it later. Questions before we wrap up for lecture 1 of today? Great. Take a 15-minute break and I'll see you over in lab in a little bit.